Okay, so when we say that a bond is polar, what we mean is there's not an even charge distribution within the bond. So the greater the electronegativity difference there is between the two elements forming a bond, then the more polar the bond will be. So the greater the electronegativity difference, the greater the polarity or charge differential of the bond. So let me just greater electronegativity difference. So again, you can do this with using like the numbers if you like, or you can actually just sort of use relative position on the periodic table, whatever you prefer. So obviously between the same two elements like we have here for chlorine and chlorine, right, you can't have an electronegativity difference between the same element. Okay, so whenever you see an element bonded to itself, there's zero electronegativity difference, so that bond would be what we call non-polar, always unnegotiable. Okay, but obviously, with all other things, we have degrees of polarity. So the general rule is if our electronegativity difference is less than about 0.5, we would say that is non-polar. Okay, an easy way to remember this is that in organic chemistry, the carbon-hydrogen bond is considered to be non-polar, otherwise organic chemistry would be very different. So look at the difference in electronegativity between carbon and hydrogen, right? 2.5 minus 2.1 is 0.4. So 0.4 is definitely considered to be non-polar. Okay, so anywhere between like 0.5 and like 2, generally speaking, is what we'd consider to be uneven sharing, so in the range of 0.5 to about 2. So we'd call that a polar bond. Okay, so it's still a covalent bond, but the sharing is unequal. With one of those two atoms forming the bond is an electron hog. And really, once you're getting to bigger numbers like greater than 2, you're probably actually looking at an ionic bond, which has complete separation of charges to ions. So another way to sort of remember which elements are more electronegative and stuff and think is to think about, hey, do these elements like to form anions, right? So because the extreme end of this bonding spectrum is that electronegative element fully takes the electron to itself, which would mean it was forming an ion, right? That would be electron affinity. So probably ionic if we've got an electronegativity difference greater than 2. But do sort of apply a little bit of caution with using like absolute numbers, okay? So we're looking at the carbon-oxygen bond. So carbon and oxygen in the periodic table, they're fairly close to each other. Oxygen is going to be more electronegative than carbon, okay? So out of the two of them, the more electronegative atom is oxygen. Okay, so we can actually represent that with a delta minus and a delta plus. You might have seen that before. So I don't have a delta. I guess I can try and draw one. We'll see. So this would be the delta minus, oh, little mini delta end of the bond, and the carbon will be the delta plus end of the bond. Okay. Another way you might sometimes see that represented is an arrow pointing towards the negative end of the bond, and a good way to remember which way that arrow points is to give it some fletching that looks like a plus to remind you that the bottom end of the arrow is the positive end of the dipole. Okay, so yes, the oxygen is more electronegative than carbon, so the carbon oxygen double bond is polar. The more negative atom is oxygen, so it's always going to be the one that's to the right in the periodic table or towards the top of the group. The highlighted bond is non-polar as the other option, so it's definitely not that. If you wanted to work out the electronegativity difference, if you're a numbers person, oxygen has an electronegativity of 3.5, carbon is 2.5, so 3.5 minus 2.5 is 1. An electronegativity difference of 1 would definitely put us in that polar range. So polar, covalent. I'm going to add the covalent just so you guys don't get confused. Covalent. All right. Non-polar is like pure covalent. No uneven sharing. Covalent. Can't spell. All right, so what's the other one then? The chlorine-fluorine bond. So chlorine and fluorine on the periodic table, both on the far right, okay? So we should expect some amount of hogging of the electrons by the fluorine, because fluorine is super electronegative. Chlorine's electronegative too, but fluorine is just so much more electronegative than chlorine. Like the electronegativity difference is 1 again. 4 minus 3 is 1. So the fluorine will be the most electronegative atom in that bond. Should check that as well. So yeah, again, if you're interested, the electronegativity difference is 1.